it's my great pleasure to welcome Wenjun Yu from Tsinghua University in China, one of the elite institutions in China, who will speak about a topic that closely kind of relates to work that is being done in our group. And he's done beautiful work on shadow estimation in the past, like in particular robust shadow estimation, and also work on Hamiltonian learning, both topics, both being topics that we intensely work on. I should say that he's also an undergrad student, so it's quite remarkable that he's done all this work being an undergrad so far. So that's quite wonderful. So I keep it short. So with this, I would like to hand over to you, and we're very much looking forward to what you have to say.
Okay, thanks for the introduction, and I'll share the screen. So can you see this?
Yes, we can see this. So yeah, that's the most spoken sentence, right? Can you hear me? Can you see me? Can you see my slides? But we can hear you, see you, and even see the slides.
Okay, that's great. And so today I will introduce the recent work done by me and Xiaoyan and other courses. And this is some new proposals to learn unknown Hamiltonian. So today I think the major concentration is about Hamiltonian learning work. Okay, so as we all know, we might notice that recently we are experiencing rapid development of the quantum technologies, including that there are so many wonderful work and proposals or roadmaps toward larger and larger quantum computers and well qualified quantum technologies, and this includes some well-known work like Google's supremacy and like IBM's roadmap and some ion traps proposal and even some Rydberg's items experiments, and but we are still in the niche area without a capability to realize a universal quantum computers, or we can even harder to apply some large-scale quantum application of quantum algorithms. So, in order to further upgrade the ability or to expand our ability in the near-term quantum algorithms, or to realize or to construct some real quantum devices, so we need a better understanding and control of the underlying quantum systems. Therefore, a natural idea is through the detection of the Hamiltonian. Namely, we can learn an unknown system through the Hamiltonian, the underlying Hamiltonians. And this is actually because of the Schrodinger equations. We know that Hamiltonian can always define the evolution of a closed system. So it actually faithfully reflects the underlying dynamics and some interactions or some properties of physical systems. But this is from maybe a more physical way. Can we be even more specific that in quantum information field, how can a Hamiltonian or learn an unknown Hamiltonian from an unknown systems how can this help? So I think that comes mainly from three fields. So first, it is from the digital quantum processing. If you have some digital quantum processors and you can learn the Hamiltonian precisely or accurately and in a very efficient way, then I think that might be a very good verification of the quantum processors. And also, you can use the Hamiltonian to learn or calibrate noise hidden there. As we all know that an arbitrary quantum noise will need exponential number of parameters to describe. So I think it will be a very good question to ask that if we have the information about Hamiltonian, can we find a natural reference so that we can use more condensed information to depict the noise. So that means that gives us an opportunity to learn or detect the noise or detect the error effects in a very efficient way, and this will be very meaningful if this can be done. Also, we need to verify the quantum simulation. So quantum simulation is aiming at using some controllable quantum systems to simulate the evolution of some environmental systems. So in this test, if we want to verify that what we have done is very good and is what we expected, then verification about the Hamiltonian of the quantum simulator is necessary and important. Also, we may use a Hamiltonian to improve our quantum sensing technologies. As we may know that the recent quantum sensing technology is based on maybe some indirect measurement or indirect observation about the change of the system's Hamiltonian. So we can to maybe infer the environmental change. So if we can have some ability to monitor the Hamiltonian, the sensor's Hamiltonian, and we can track the change or modification in a very direct way, then this can help us a lot to use this Hamiltonian as a sensor to sense more or more complete view of the environmental systems. Okay, I think these are several ways that if we have a very strong Hamiltonian learning protocols, what can be done? So besides or before this, let me introduce a more specific definition about Hamiltonian learning. Hamiltonian learning is aiming at estimating an unknown Hamiltonian given the control of the Hamiltonian evolution. That means we can control the Hamiltonian evolution time, and we can decide where to insert the Hamiltonian evolution in a quantum circuit or in your protocol. And in this paper, we focus on the Hermitian Hamiltonian, and we want to decompose it in the Pauli basis. So there we have a Fortuitian real parameters, and we call this the decomposition parameters. So therefore, Hamiltonian learning, oh yeah, sure.
Can I ask you a question? I mean, here and also in your paper, you don't make any further assumptions on the Hamiltonian, right? I mean, you have a full Pauli basis and expand the Hamiltonian in the Pauli basis, but you would not think of a, say, concept class of Hamiltonian that's kind of nearest neighbor-like or has other like meaningful features.
It's partially right, because we don't make any specific assumption. So that means that we may assume that these Fortuitian parameters will be sparse. We may assume things like that, but we don't impose some assumption like it is a Ising model or Hubbard model, or it is near neighbor. We don't assume that.
Okay, wonderful. Thank you.
Okay. And
may I
so,
also ask a question?
Sure.
The constraint of the parameters being real, is it crucial, or is it more like to boil things down a little bit?
I think for now, since I'm also considering these questions to rule out this Hermitian assumption, but I think currently I am not sure that this can be done very trivially. There's some other questions toward non-Hermitian Hamiltonian.
Okay. Oh yeah.
Okay. So therefore, we have convert the Hamiltonian learning to some signal learning problem or some parameter learning problems, and we want to solve these questions by executing some quantum circuit and measurements. So as I said, that Hamiltonian learning is a well-known problem, and there are serious profound papers that try to solve it with different types of efforts. So let me introduce several representative papers. So first, Nansen Weber and the co-authors proposed the ontological evolution, and it tried to use some inference method to learn the target Hamiltonian. And that I think is very inspiring, that to inspire us to use some inference or some Bayes inference things like that to try to learn the Hamiltonian. And I think several other works are based on these papers. Another type of scheme just assumes that they have some eigenstates or thermal states of the unknown Hamiltonian, and this Hamiltonian, of course, contains the information. This state contains the information of the Hamiltonian, and by measuring these states, they can get the information and to recover the Hamiltonian. This is also wonderful, yeah. And the third type is some algorithms that are based on specific assumptions, like they have some local term or near interactions, and also Yan's new paper is also, I think, belong to these types because they assume the superconducting oscillator. But of course, it is true because they just implement this algorithm in the experiment systems. So the fourth one is some proposal that trying to recruit some classical machine learning ideas to acquire information from direct state preparation and evolution and measurement process. So all of these are interesting and wonderful and actually very inspiring, as at least for me, and maybe when I'm trying to solve this question in a practical and efficient way.
Another comment, maybe. I mean, not all these papers would make use of time evolution, right? I mean, there's also some that would use other information, like information about Gibbs states and so on, while most would like prepare certain states, would evolve them in time, would perform measurements. Are you commenting on that later, or is that continue?
Yeah, yes, but you mean most of things will use the thermostat, right?
Yeah.
But, yeah.
No, never mind. I mean,
that's true.
Yeah,
that's
there's
true. I think
ways
that,
to kind of acquire information about the Hamiltonian.
Okay,
thanks.
From these previous efforts, I think we can be more clear about what we want or what a good algorithm will be like. So I think firstly, it should be universal. That means we need to, the algorithm is supposed to be able to recover all the Hamiltonian in all in most situations. And the second one is that we want the protocol to be efficient. At least the complexity must be polynomial to the size of number, a QMIO number, and it is supposed to be robust so that we can be noise resilient to some spam errors. And if you want to introduce some circuit component, then the circuit noise must be considered. And it should be practical, namely that we cannot assume some miracle component that you cannot achieve in near-term quantum computing. So I think our work just achieved all of these four criteria, and I think that is the reason that we claim that our algorithm is practical and efficient. Okay.
Sorry.
So before we,
Can you say, or will you say some more about this extra circuit that you mentioned? So what does the circuit noise correspond refer to the noise of the implementation of the Hamiltonian, or?
No, not the implementation of Hamiltonian, but in this protocol, we will introduce some circuit component like some gate things, polygate things. And if you want to introduce these circuit components, then you have to try to rule out the circuit noise. And that is why we include the circuit noise part.
I see. So because I mean, in your scheme, you're like specifically doing like a poly twirl, right? That in each step you really have to do. It's not only a post-processing step, but you're really literally poly twirling, right? And this is the step that has to be robust, right?
Mm-hmm.
Okay.
Yes.
Mm-hmm. Wonderful.
So before we move on to the main result of our work, we have to introduce some assumptions, and that will just answer the question Jens proposed. That firstly, we have to assume that the composition parameters are sparse. So the non-zero parameters is the number of non-zero parameters is polynomial with n. And this is because that if you have actually 4 to the n parameters, then the complexity will always be exponential. So the other thing is that regarding these non-zero parameters, we have to lower bound these terms by some constant so that we can always be able to distinguish the meaningful non-zero signal from the noise effect. And we have to expect the circuit noise and the span error perform binarily so that the effects are smaller than some threshold from making the protocol crash. Because this is something very similar to some RB's assumption, as we may know that the noise and the span will not be cannot be unboundedly enlarged. Okay, so we have the following theorem that we can prove rigorously. So it says if all the assumptions hold and we choose a series evolution time with a typical unit time t0 for some fitting process, then this Hamiltonian learning algorithm can return all the non-zero parameters up to this accuracy, and also we can return all the perfectly correct support estimation of which is non-zero and which is not. And the procedure to achieve this accuracy, we have to pay for some circuit measurement complexity and classic computation complexity, but both of these are maybe polynomial with the system size and the sparsity of the parameters. Okay, so is this part? Is anybody have some question towards this part? Okay, great. So maybe
the the scaling in epsilon, that's maybe the kind of the toughest scaling, like the weakest link, so to say, right? Is this tight? I mean, this this epsilon to the power of -4. Will you comment on this? Is there kind of an aspect of the proof you're using, or is that like an inherent feature of your protocol?
I think the epsilon to the -4 is from some channels property. Since the Hamiltonian evolution channel is not the Hamiltonian operator itself. So we have some relation between these two things. If you want to use some channel estimation protocol, then you need first estimate the Hamiltonian evolution channel. Then from the channel, you get the Hamiltonian operator. And that is the reason that we have additional scaling.
I see. But then, I mean, also viewed from this perspective, it wouldn't help so much to like make strong assumptions on the Hamiltonian, right? I mean, for example, to be nearest neighbor or so. I mean, that would simplify the problem, but the scaling in epsilon would be quite similar in that case, right?
That's the case. If you it is not so clear that if you make some further assumption, this will help. So yeah.
Okay, thank you. That's insightful.
Great. So besides the theoretical result, we had the simulation results, and for the simulation, due to some device limits, we don't actually faithfully track the circuit execution. Instead, we use some oracles to return the circuit measurement with some artificial random noise, and we use this to simulate the performance of the circuit measurement. So as you can see here, we will use the calls to the oracle to represent the complexity, the circuit complexity. And I think that can shed some light on the scaling property of our algorithms. And here, this diagram just illustrates the scaling property of our algorithms on some transverse field DC model Hamiltonian estimation. So here we run the algorithm from single qubit system to 7 qubit systems, and for each qubit, we randomly sample 50 sets of random parameters for the Hamiltonian, and for each Hamiltonian, we independently run for 10 runs. So altogether, for each item, we have 500 cases here. So now the question is, what is this? What are these items? So these items are actually, or this figure is actually named the Wilding plot, and each item is of course the Wilding. So this Wilding actually depicts the probability density function vertically. So you can see the so here the width actually depicts the probability for the thing happens in the level. So you can see the blue Wilding just illustrates the arrow for this 500 execution, and the red Wilding just depicts the number of oracles we need in the execution. Okay, so I think this Wilding plot is really tough for understanding. So if you have some question here, you can directly ask.
Maybe a kind of a soft question, which I mean I've also asked this before. I mean the relatively small system size are just a consequence of the fact that you wanted to run this on a laptop, right? I mean this would also work for larger system sizes, right? Because it's rather efficient and would also work for larger systems. Okay, and will you kind of comment more on the scaling of the error with n? I mean, like discuss more what happens for large n.
Sure. For large n, actually, you can see here it is obviously not linear scaling, because that is because the parameter s here. So s actually depicts the sparsity of the non-zero parameters. So for each TFIM Hamiltonian, we will have s to be linear to n. So altogether, the complexity is quadratic things. Okay. And here you may see there's a huge gap between when the qubit number is very small, and I think that is because actually if the qubit number is small, then the 40n is also small. So actually, in these cases, in this region, we have we actually emulate all the 40n fortune parameters, or fortune some do some exponential things here when the n is small. But when the n is larger, then this will just return to the polynomial region, and that is why you can see here maybe when n is really small, there's a huge gap to the n is comparably larger.
That's interesting. Thank you. I see.
Okay.
Can I ask, what's the stopping criterion for this? Because the number of the calls to the oracle, refers to essentially the number of times you have to do your experiment, right?
Yes.
So is that the number of experiments you need to do in order to reach the error that you want to reach, or like what's the stopping, what's the convergence criterion?
Yes, this is an interesting question, and I think I can only partially answer this question at this time. So I will introduce some more detail about our protocol shortly. And here I will say that the criteria to stop is when you use several you will use several different independent rounds of some subroutines, and you just think the procedure will think that all the non-zero terms are extracted, so they just help. They are hot.
So that means when you have identified all non-zero terms, essentially.
Yeah. Yes.
I see. So this means. Sorry.
So if you can imagine that you have a hash function and you have a very sparse exponential vector, and you just randomly hash these parameters to some different things, and so for each round you have different kind of hash function, and this hash function is randomly chosen. So you have some different execution results, but overall you can always extract a larger part of the non-zero terms. So you can overall you can have a pretty fair results.
Okay. Can I ask also, what do you think is the number of calls to the oracle? They increase when you increase the system size. Of course, you need more. You need to do more experiments to find all the non-zero parameters. But how do you expect this to continue? Is this going to be linear?
Yes, from the statement it will be linear. But if you have some Hamiltonian with increasing size of non-zero items, then this will not be linear. This is linear with S and N respectively.
Right. Okay.
Okay.
Thanks. Cool.
And besides this overall overview of the scaling properties, we have some simulation about some single shot cases. So first, we have a 7-qubit TFI and Hamiltonian with randomly picked parameters, and we can see here all the estimation performs well, and we also perfectly estimate all the sign information with these parameters. So I think that is really a great results for our algorithms. Here we artificially add 10⁻³ noise, Gaussian noise. So and you can see the recover noise is also remaining in this region, this magnitude. And we also to verify our method for an 8-qubit molecular Hamiltonian. So this is this Hamiltonian actually contains 184 non-zero items on zero parameters, but here we only exhibit the top 50 terms, and you can see most of these parameters are estimated really well, but we have some maybe bad dots or something like that, and when we examine this thing, it is because of the flip of the signs. So in some rounds we estimate it with a correct sign, but in some round we estimate wrong. So so average these values, we will get a very huge fluctuation, and this is not essential but we want to just keep this because we want to say something from this bad dot that when the signal or when this parameter, the absolute value of this is getting smaller, then we have a larger probability to estimate it wrong.
I mean, there's this funny point where the accuracy is very different from the others. Will you comment on this?
Yes. So I'm not sure.
No, I mean, there's this outlier at one of the Pauli indices with signs. That's where you have a kind of bit of a jump.
Yeah, we have some. As you can see, we add the sign here, but in some case, we add the sign wrong, or we estimated the sign wrong. So
I understand. Okay. Mm-hmm.
Yeah. Okay, great. And these are all the results that shown in our papers. So what is the protocol? Actually, the protocol is a very important thing, as that answers a lot of questions that you may remain in the last phase. So I will just first give some preview of the protocol. Our Hamiltonian learning is actually inspired by the quantum channel estimation, and the reason that we want to use this idea is because we want to achieve the universality. So if you want some universal proposals, then you will always to consider the general or an arbitrary Hamiltonian channel. So this is I think the premise that we use the quantum channel estimation. And also, we will use a composite algorithm to first estimate the absolute value and then to estimate the signs. And the reason to divide this is because we want to keep all the things span free. So for this first stage, if we want to keep this span free, then we can directly use a very similar idea to the randomized benchmarking protocol. And for the second one, since we only need the sign information, and this is some discrete information. So if we can keep the noise effect as small as possible, we can always keep the sign from flip. Okay. So great, and even though we divide the protocol into two parts, we actually implement 3 subroutines to construct the estimator. So the first is actually the RB circuit to estimate the polyfidelity of the Hamiltonian evolution channel. And the second one is some transformation from the polyfidelity to polyerror rate. And we will show that these two will combine, can serve as the absolute value estimator. And the third one is some process tomography, very similar to that manner. And we can use this process equation to solve the sign information. So first, let us view the expansion about this poly evolution channel. As I have said, we have to figure out the relationship between the Hamiltonian channel and the Hamiltonian operator. So in in this expansion, we can see that for all the higher order terms, there are some parameters hidden there. So for the first order term, we have a linear relationship with the parameters, and for the second order term, we have this quadratic things. However, since we want to use the randomized benchmarking, the constraint is that we can only focus on the diagonal part of this channel, and this is a property inherent from the randomized benchmarking proposals. So, what is the diagonal part for this Hamiltonian evolution channel? We'll find that, fortunately, these diagonal parts actually depict a link or construct a very simple and direct relation between the decomposition parameters. And that means if we can get the diagonal part, or namely the polyerror rate of the Hamiltonian evolution channel, we can actually get the square of the desired parameters, and that is actually the absolute value of the decomposition parameters. So the question just is reduced to learn this polyerror rate in this stage. So we will use these two subroutines successively to try to extract this polyerror rate. The first one was proposed by Steve Lamia and Joe Woman in 2019, and this is this proposal was actually aiming at estimate the implementation noise of polygate. And as you can see in this circuit A, it used some polytouring to convert the implementation of noise to a polychannel, and it used some very similar to the standard RB manner to extract the polyfidelity of this implementation noise. So the polyfidelity is actually defined as here input poly operator and measures the same poly operator. Yes. Maybe there is some normalizer here. Here we want to adjust.
I asked this before, but I mean,
Yeah.
This is really something you can't get away from, right? I mean, you really have to do this twirling. So that means you cannot kind of conjugate the polys through or something, or do a different post processing. So that one must have like the experimental capability of performing polys along the way.
Yes, exactly.
Okay. Thank you.
And to just to try our best to make this practical, we can claim that all the things is local gate. So at least this can be easily implemented in some computation devices. Okay, so since here we want to estimate the exotic Hamiltonian evolution channel instead of the implementation noise, we have to adjust the protocol a little bit and to employ some ideas similar to the interleaved randomized benchmarking. That is, we use another round of estimation, and here we insert the Hamiltonian evolution in the loop, so that first we estimate the implementation noise information, and then we estimate the composite channels information. And by do some post processing, we can get the information about the Hamiltonian channels purely. So from these two circuits, we can get a noisy polyfidelity of the Hamiltonian evolution channel. Yeah, sure.
Can you quickly explain what the lambda C and lambda P respectively are? Maybe I missed that part. Like how are they?
Lambda. Oh yeah. So the number C is so here we have to do some state preparation. So we use a Clifford gate to represent this state preparation. And when you do the state preparation, you have some noise or have some errors, and this is implementation errors. And also similar, this is the implementation error of the span of the measurement. And the lambda P here is when you introduce the polygates, the gate itself will bring some implementation noise, and this is a gate noise.
Okay. So, but does this mean that you use only like on-site Clifford operations for the state preparation plus some noise, or is this just the image, but in principle you use any whatever for the state generation?
We only use a local Clifford here. Yeah.
Okay. What type of interleaved RB do you use in the analysis? Because like, the standard interleaved RB kind of like, it's completely not interpretable in terms of fidelities.
Yes, that is a really critical question. And as we cannot claim that in general we can recover all the information here. So here we have to impose some assumption that this number P is self-stochastic. So it is self a poly channel.
I see.
Okay.
Can I? Sorry.
Sure.
So in principle, you want to implement the twirled version of the Hamiltonian channel, right?
Mm-hmm. Yes.
So
yes.
And is that done by doing these Cliffords before and after the application of the Hamiltonian channel?
It is actually done by the randomly picked polygate.
The C gates, the Cliffords that you mentioned, right?
Oh, no, it's a P gate.
P.
Yeah. Here we have some.
Okay.
Yeah, this loop.
The blue gates, but I thought those are the ones that you measure, like in your expression above F alpha, that's where you pick a Pauli and then you say you want to estimate the Pauli fidelity for one specific Pauli.
No, yes, we want this fidelity, but this fidelity is not actually directly measured, since we cannot actually input the Pauli operator. So here we use this random polygate to cool the Hamiltonian, and we will track the exponential decay to feed these terms. Okay. Yeah.
Oh, okay. Thanks.
Okay, great. So far we have some noisy polyfidelities, but what we want is a poly error rate. So to transfer from the fidelity to the poly error rate, we have to find out the relationship between this. Actually, the transform is named as Wash-Hadamard transform, but it is intrinsically exponential transform, as women. That means we need all the 4-to-the-n poly fidelity to calculate every single poly error rate. But this is unaffordable since we want a very efficient protocol. So here we will perform a trick to simplify this transform by some coarse grain calculation. That is to say, we will choose to to estimate a subset of the fidelity terms and to perform a very similar transform so that we get effective polyarray rates. While this polyarray is actually some linear combination of many real polyarrays. So you can imagine since we have the polyarray itself sparse, that means if we have some combination of the polyarray, then we can expect this only contain very few non-zero terms. So even if we perform it smartly, we can even control it to contain only one or two non-zero polyarray in this p hat. So this can help us a lot in the sparse case, and we can directly extract all the information of every non-zero polyarray from this coarse-grained effective P. And to be more clear, I will show some GIF here to illustrate the things. Well, so first we will use a subset of the fidelity terms to construct the effective P, and it is like this. Here we use different subset of the F to construct two group of P, and each P is actually so each P here is just a row of this array, and as you can see, in the first P, we have only one non-zero terms here, and we will observe that the absolute value of this is remains the same. So we can guess that it contains only one non-zero terms. But in the second one, we have different absolute values here. So we may say that it contains multiple non-zero terms. Oh, sorry. So we have the following guess. Well, by witness the signs of the values, we can learn the index of the poly. So we can have this pxx equals to 0.5 from directly the first effective P. But from the second one, we get nothing. And that is the reason that we will use a second group of samples. And from the second one, we can get a very similar gas here from the third effective P. And we will find the PIZ equal to 0.2. And since we know that PIZ is supposed to be in the second P, and we know the underlying polyarray in each effective P, but we don't know which term is non-zero and which is not. And we know that PIZ is supposed to be in the second one, but we don't know this is non-zero term. But here we know, so we can just replace this in the second effective P, and we find the P. The remaining thing is some single term, and we can get the PYX equals to 0.3, and we then replace all the things to the last effective P, and we find that all the things is resolved. Yeah, I'm trying to make things clear, but this thing is actually essentially complicated. So if you have some questions or you can't catch this, you can just ask some questions.
Yes, I would like to. This fast transform is defined through this embedding phi, or embedding is maybe the wrong word, but this function phi, right?
Yes, you mean the sample, this phi, right?
Exactly, yeah.
Mhm.
Is this phi something you have to put into your algorithm, or is this like there is some phi that works for anything?
You have to randomly choose some phi, but this phi is actually some, as you can see, it is some. We choose this to be some random binary matrix.
Okay.
So you can just extend the B bit strings to a 2n bit string.
Okay.
And
this binary matrix is sort of, it's essentially like an embed, like just okay. And okay, because like what you just showed with the glasses and so on, I think like how whether this works or not depends on the phi respectively, right? And then I
yes,
suppose that with
exactly.
each randomly drawn phi, you get with like a certain probability that the next round will satisfy what you just explained, and then like recursively you get like better and better.
Yes,
like,
actually.
Okay. Thank you.
So we have some, actually we can prove that if you randomly pick this this phi in a random binary matrices, then you can the process can be performed it's perfectly, and you can extract all the non-zero with a vanishing failure probability with yeah.
Cool.
I mean, there in classical signal processing, there are also techniques to calculate a sparse Fourier transform, like going back to Gilbert and Trop. I mean, this looks pretty much similar. I mean, there you do like dilatation in order to like scatter away like your sparse support even more, which I think you don't do. But I mean, like the thing of like tapping coarse graining in different in random permutations, and then like I mean seeing then trying to get away with only one support with high probability per tap. This is kind of like the same idea here.
Yes, quite similar. Actually, the fast transform formation, the idea is we are much inspired from the classical condensed sensing method, and the signal processing is just remain, or the idea remains the same, but in the quantum version we deal with the noise terms. So if you have some noise here, or the F are not ideal and P is not ideal, then how can you deal with these things?
No, but I mean, okay, this is okay. Then maybe I didn't get the point. I think this is now just like to get like the sparse coefficients of like a Fourier transform, a Hadamard-Wald transform, like Fourier transform over F2. So like I mean, what you need in order, like I mean, okay, you get your data from like your Steve's types of Pauli benchmarking, and then you need to calculate one Hadamard-Wald transform in order to get like the Pauli coefficients per fitting, correct?
Yeah.
And this is kind of like disentangling like the diagonals of like your noise channel or like your Hamiltonian. This transformation. And now, I mean, okay, and there are techniques in classical signal processing in order to calculate, I mean, for the standard Fourier transform, I mean, if you know that, I mean, you get sampling access, and sampling access is now like, I mean, you can choose entries of like a signal which is sparse under the Fourier transform, that then you can like efficiently estimate the support of the techniques. And I mean, I think these techniques are kind of like similar to what you're doing here, but I mean, I'm not sure about this. So this was kind of the question.
Because I'm not sure what about disentangling, since but I think what you described is some classical method that try to do the discrete Fourier transform efficiently and fast. And I think since the question itself is actually very similar, the Wash-Hamilton transform and the discrete Fourier transform, are very similar. And actually, this protocol is inspired by some classical signal processing methods. So I guess that you're right. These are very similar.
What are the classical processing methods? I mean, what you're mentioning?
Actually, this algorithm is classical, right? As you can see, all the things remain classical.
Not the inspiration. Like, I mean, you were referring to classical signal processing methods for the inspiration.
The original idea is from some 2050 papers. But if you want, I will show you. But here we use this to the things or the update we made is just to try to make the idea from the signal processing to feed the noise circumstance in the channel detection. So in that classical version, they don't consider so much or so practical noise assumption. They just assume some Gaussian noise. But here, in order to serve as a subroutine in the whole estimation, we have to make the noise to be more practical as what it will be in when you are processing some circuit measurement.
Thank you very much.
Can I ask quickly? This p hat, that's the object you're measuring, right? Because you said before we're not measuring the Pauli fidelities, but we are measuring these coarse grain fidelities, right?
Yes. So this is the original one, and this p is what we want. But here we use the p hat to. But a single p hat contains so many polyadder rates. But fortunately, we have the sparse assumption, so yep. we can always extract the sparse information.
So the circuits you showed, they estimate this p hat, right? Is that?
Oh, you mean this circuit? You mean this circuit?
Yeah.
This circuit estimates the fidelity, and you use a subset of the fidelity to sum up to this effective p.
Oh, okay. So you do measure the fidelities, but then from those you estimate your bins, the PJs.
Yes, exactly.
Ah, okay. Okay, thanks.
Great. And so let's move on. So the only thing remaining is to estimate the size, since we have already estimated all the non-zero polyadder rate, and this polyadder rate just reflects the square values. So to fulfill the estimation and to estimate the size, we will use something that's really similar to the process tomography things, and we will directly input the state and to do some evolution and to do the measurement. So we can construct these equations for each pair of state preparation and measurements, and we can construct some equations, and we can go even further to do some linear regression to rule out this T effect, and we can construct this kind of equation here. As you can see, this is a linear equation, and we can directly solve this by prepare several states and do several measurements. But here, important question is that here what we use is some information from the stage one. We know since from the stage one we know which items is non-zero. So here we can reduce the size of problem from exponential to the polynomial. So here we only care about those terms which is underlying non-zero. So this is a polynomial size problem, and we want to do this. We want to construct this equation and solve it. But the question still remains that how can you perform robust in this case? This direct state preparation and measurement seems vulnerable to spam errors. So how can you perform robustly? The idea is to use some random input and random measurement to make the coefficient matrix here, or the coefficient from the equations, to be robust. This makes the matrix possess approximately restricted isometry properties, and it is some idea from the compressed sensing method, and it says that if you have this random matrix, then you can always bound the error from the observation, from the measurement, and in the process of solving this equation, you will not enlarge the error effects. So with this, we can only say that we bound the effect of the noise, but we cannot say that it is robust. So another idea is that since here we only want the sign information, so if the noise effect is not so large to make some of the parameter flip, then this estimation is intrinsically robust against these errors, and that these two things help to make our stage 2 stable. And so far we have all the sign information with the absolute values so that we can fulfill the estimation. And this figure just depict how we execute and how we implement the protocol. So in the stage 1, we do some RB circuit and get the fidelity, and we do the beam detection, or we construct the effective P to find all the sparse terms. And in the stage 2, we directly prepare and measure some states, and we solve the equation to get the sign information. And combine these two, we get a whole estimation of the decomposition parameters. Okay, great. And so in this work, we actually provide a scalable and a practical Hamiltonian learning method, which is really robust against both the spam errors and the circuit noise. So can we go even further to estimate some non-sparse Hamiltonian? That means we can give, if we know that some Hamiltonian contains some unevenly distributed parameters, then can we do some estimation rigorously on this Hamiltonian? And also, I think some interesting problem remains that if we have some really strong Hamiltonian learning method, can we do better in the whole field of the quantum computation? Just like what I mentioned previously, can we do some verification, do some noise detection, and can we even improve the techniques of the quantum sensing? I think that those are very interesting problems. Okay, and thanks for your listening.
Thanks for the wonderful talk. That was great. Yeah, we had loads of questions along the way. Maybe there's more. Are there any questions or further questions?
Yeah, maybe a short one. Thanks for the nice talk first. so the assumption that all the gap that all your non-zero Hamiltonian parameters are larger than some threshold, that would, if you didn't have this assumption, you would get a problem with sampling your Pauli fidelities, right? Because then you couldn't estimate these bins from your Pauli fidelities anymore. Is that correct?
Actually, the problem remains in this step. So if you have some really small value, then since here we don't show the noise, but actually there are some noise effects in every bins. So so if you have some noise, you have some noise and you have a very small value, then you can figure out, or you can distinguish this real signal from the noise effects, and you will just say, oh, just let them go, and you don't try to estimate these small terms.
But even without noise, because you're in principle, you're not able to measure all Pauli fidelities, all 4 to the n Pauli fidelities, right?
That's true.
So even without noise, you would not. Yeah, there's a chance, like if you have a very small parameter, that this just doesn't show up, right?
If you don't have any noise, then you don't need to estimate orders of fidelity. You just use this coarse grain calculation. You use a subset of fidelity and you construct this structure. And in this structure, if you don't have any noise, then for arbitrarily small value, you can assume this as noise. So you have to figure out what is this, and this will help you to extract all the small terms.
I see. So does that mean the size of the noise tells you how small the threshold is for your Hamiltonian?
Exactly.
Okay.
Maybe a high level question. I mean, I must say I really love this project or this paper. That's really super interesting. So I mean, in a way, it's like a very cute combination of regression and sparse Pauli channel learning that you pursue. That's really a good idea. Can I ask, like, I mean, how does this compare to like other schemes that make use of like similar ideas? I mean, there's this paper, for example, by Ha, Rotari, and Tang that do like learning of quantum Hamiltonians, but not from time evolution, but from high temperature Gibbs states. But in some way, what they're doing is kind of similar. Can you relate your work with the Ha, Rotari, and Tang work? Also in terms of sample complexity?
Actually, I just read that abstract, and I don't go through that paper. But I have some questions that if you want to prepare some Gibbs states, then is this will this state be really accurate or too precise enough?
Oh, that's a good question. I don't know. I mean, I wouldn't know. Besides, it's maybe also not, I mean, not so practical to prepare Gibbs states at different temperatures. I wouldn't quite know. That's right. But it's that paper is interesting, like technically interesting for the bounds on sample complexity. But I do agree, if that's your point, that it's also obvious to prepare like high temperature Gibbs states at different temperatures. I would say.
Wouldn't that correspond to putting your thing, whatever the Gibbs state corresponds to, into a different room with different temperature?
Yeah, that would correspond to that, yes. But you need lots of rooms then.
Well, or you have to have a controllable heater.
Yeah, that's right. No, of course. I mean, yeah, that's right.
I have another question. I mean, concerning like, I mean, the practicality on like actual machines of this scheme. Because I mean, all these randomized benchmarking techniques are super tailored towards like digital quantum computers, where you have a fair control and you can think about gates and I mean, the thing you are actually interested in is not like Hamiltonians, but it's actually gates that you do. I mean, in the end, like, I mean, you learn literally do like a tomography method for like, I mean, a channel, and then you relate this to the Hamiltonian parameters by expanding it for small times. I mean, how realistic is to actually do this on an analog simulator? Because an analog simulator is a very different beast. It's kind of like a device where I can dial in a couple of parameters, and then there's a time evolution, which I have super high control, and it will just run, and then I can measure something. But I typically don't have the freedom to turn on my Hamiltonian quickly, turn it off again, turn on, turn it off again. Because I mean, the reason why digital computers work is already that kind of like the effects of the turning on and off is already included in calibration models and so far. Yeah. So like, I mean, how realistic is it actually to even have this type of control which you need for protocols on an analog simulator?
Well, this is a very good question, since and this is based on our assumption for our protocol itself that we have to use some gate component, and this is the first. And also we have to successfully turn on and turn off the Hamiltonian evolution. And I think that if you want to just to adjust this protocol to make it possible to implement in some analog simulator, then I think the first thing is to get rid of this the first RV circuit, and to try to use another circuit to estimate the fidelity terms. And I think this might be possible if you can use some direct measurement to estimate the fidelity. Then that will be helped. But if in that case, you cannot claim that you are spam free. But I think that will be okay, since in analog systems, spam errors might not be so important.
I would argue that, like, I mean, also from my experience, like the spam errors in analog systems are of another nature. Like, I mean, the turning on the Hamiltonian and turning off the Hamiltonian is literally the spam error in an analog simulation. This is kind of like, because I mean, all these things happens fast, but not instantaneously. And I mean, you get considerable rotations with this. So, I mean, when you say like a spam-free Hamiltonian learning, I would say, like, I mean, here it's more realistic to even like see like the spam as happening in every step, because you always have to control your Hamiltonian and control it back again.
Yeah, so
this is kind of,
well, that be that is it fair to call that spam errors, since that seems like some control errors, right? You turn on and turn off the evolution.
Yeah, this depends on what you want to call, like, I mean, the evolution, like the thing which actually, I mean, is kind of like under control and implementing what you do. No, I mean, I'm totally fine with, like, I mean, saying that it's kind of like, yeah, what you call this or this is kind of like open to debate, and what is practical is, like, I mean, super. It also is, I mean, okay, for a digital computer, I mean, this will be a super good method for learning Hamiltonians. But yeah, okay, call it control errors. But I mean, kind of like the only thing which happens, because like in analog simulations, to my experience, is exactly these type of controls. These are like the most dominant errors. So therefore, like, I mean, assuming super fast control or like perfect control, and then having like a protocol which uses like, I mean, a lot of control sequences all over, I mean, it's kind of like very far from what we can do with the current devices.
Yes, exactly. Yes. So the I think the next step we can consider that some other protocols that to estimate the fidelity, or we can even directly estimate the polyfidelity from a single time evolution, and that might be possible if you. But I'm not sure how to deal with noise and what's the size of noise it will be. So if you just give up the span-free sort, then I think you can directly estimate of that, and that will be okay. And you can directly use the other two, the other two subroutines, just to replace the first one with some direct measurement. I think that will be okay, but then you'll take the risk to undergo some noise, and I think that will be some trade-off.
Mm-hmm.
Yeah, no, I totally agree. Well, I mean, in a sense, I mean, what I find intriguing about, like, I mean, learning analog simulation is that, I mean, there's another analogy between like the analog simulation and time and RB, which is like that RB has kind of like encode decaying parameters into whatever you do, while the Hamiltonian time evolution is already like oscillating. Yeah. So there are certain parameters of the time evolution, such that the eigenfrequency, which are automatically spam robustly encoded, because I mean they change with time.
Oh, so you mean just like some method in the precise Hamiltonian identification paper, right? To use some time evolution to rule out the spam effects, things like that, right?
Yes, I mean if you would not do anything, like I mean then already like the things which change with time, like the eigenfrequencies, already are automatically spam robust. It's kind of like the same as estimating RB poles, but on the unit circle instead of like on the real line.
From my perspective of view, if you just use this equation, if you change the t, you can just imagine that it only changes the effective s. So you can regard these terms in one terms, and then if you enlarge the t, and the only thing changed is just the effective s change. And if you use different t, of course, well, I'm also sure at present that if you can use some series of time evolution to be resilient against some errors, against some spam errors, because I think that is highly non-trivial things if you want to do it. If you want to do it for an arbitrary Hamiltonian.
Yeah, I mean, okay, yeah, yes. I mean, this method relies on like the short times in order, I mean, yeah, to kind of like invert, like, I mean, the process, like infer the Hamiltonian from the process. I mean, this is kind of like here implicit by like having short times, so that I mean, I'm for every times short, I kind of have a linear inversion problem.
Indeed. So in this sense, it's like very like complementary to the approach of Frederick, right? Where he looks basically at long times and needs like a classical representation of the state to infer about the evolution.
Is this similar to your superconducting work?
No,
Hamiltonian.
With this, okay, with the superconducting work, we are in the super nice sweet spot of saying, okay, we first do the simple things where like classical simulation is not a bottleneck at all. So we can go to long times, and then we can use like the encoding in time to do this. Yeah, but I mean, you might ask, like, I mean, what do you do when you lose control over the forward simulation to begin with? Yeah, and I mean, here, like, you control this error by just restricting to short times. But like, I mean, this is what I meant with an analog simulator. Typically, I mean, you will have a very precise Hamiltonian evolution for like a given amount of time, but like the changing the control quickly will induce a lot of control errors.
Yeah. So okay.
So I mean, this is kind of like, I mean, could you go to a higher order? Like, I mean, this is kind of, could you use like longer times for your in every step?
Yes, that will be very good questions to use higher order terms, but currently actually, I didn't think it previously, and to use a higher order term, I think the question is how to extract things, all the things. So the major questions is.
Yeah, that's not
Yeah, I mean,
obvious.
you would have some very complicated polynomial equation in the S, which you then have to invert. Yeah.
Yeah. And you can discard any higher order, even higher. Yeah. Yeah. And and another thing is that how can you inverse the how can you rule out the state errors? Just like you introduced in the precise Hamiltonian identification, that you can do that in pseudo inverse, because that is, I think that is in the first excitation, the first excitation state. And how can you do this for a universal Hamiltonian?
No, we cannot. We cannot. Yeah.
Yeah.
I mean, okay, we are working on an extension on this to also, like, I mean, to quadratic Hamiltonians with some structure. So, I mean, you can think of this. Okay, this is kind of like, I mean, these type of things coming from the digital perspective is kind of like the top-down approach. You directly tackle the entire Hilbert space. While you might think of, like, I mean, start like in an analog simulation, it's quite naturally that not all states are created equal, but like states with just a few excitations, yeah, are like simpler and already per se all the information which you need about your Hamiltonian. For example, like every condensed matter Hamiltonian, it might be interested, like every textbook condensed matter Hamiltonian. You can already infer from just scattering experiment of two excitations. So this, I mean, there are ways to reduce the complexity also, like for more complicated, for all realistic Hamiltonians which appear in text.
Okay.
But I mean, yeah, thank you very much.
Yeah, these are very good points. Wonderful. Thanks for the talk again. Thanks for the many questions and discussions. So are there more, is there a kind of a final question on this also from anyone? An urgent one, a kind of an overarching one? So I think if that's not the case, then thanks so very much again for this wonderful and exciting and stimulating talk, as you can see from the many questions and the good discussions. Thanks for coming. Let's catch up very soon on this. And yeah, thanks again.